So in this part of the lesson, we're going to be looking at solving logarithmic equations. And to solve logarithmic equations, we're going to be using the properties of logs that we learned in the prior lesson. So when we solved exponential equations, we had two different strategies we used. We either used the strategy of writing both sides as the same base and then setting the exponents equal to each other, or we simply took the log of both sides. When we solve the log equations, we have basically one strategy, and it's got two steps. The first step is to, number one, rewrite one or both sides as a single logarithm. So if you have logs on both sides, try to write the separate sides as single logarithms, and then use the log properties to do that. And then rewrite the log into exponential form. So we'll use what we know about changing from logarithmic form to exponential form, and then sort of the whole solution will just materialize from there. So in example A, we're asked to solve log base 6 of 2x minus 1 equals negative 1. Well, this first step that I mentioned in our strategy was to rewrite one or both sides as a single logarithm. Well, that's already been done. So we actually are moving on to step 2, which is then rewrite the log into exponential form. So if we did that, remember we start at the base, which is 6, and we raise it to that power, and it equals the result. So rewriting this in exponential form would look like this. 6 to the negative 1 power equals 2x minus 1. Now 6 to the negative 1 power, I know that that's 1/6. So this really means 1/6 is equal to 2x minus 1. And now I can solve that just by adding 1 to both sides. So if I added 1 to both sides, that would give me 1 1/6 on this side, or 7/6. I guess you could write it as 7/6, or 1 1/6. And that equals 2x. And then we could just simply multiply both sides by the reciprocal of 2, which is 1/2. And that would solve it for x. That would tell us that x must be, well, 1/2 times 7/6 is 7/12, so 7/12. And so our answer is 7/12. If we were to substitute that back in to the original equation, it would make it true. It would give us a value for 2x minus 1 that was equivalent to 6 to the negative 1 power. Okay, so what about example B? So example B, this time I have two separate logarithms on the left-hand side. So the step number 1 was to try to rewrite that side as a single logarithm. Well, remember we learned the quotient rule for logarithms that says we can use it in two different directions. If we know we're subtracting two logs that have the same base, we can combine them together and write it as the log of the base and then of the quotient of the two separate logs. So it's going to be log base 4 of 100 divided by x plus 1. Now that equals 1. So we were able to complete step 1, rewrite the left-hand side as a single logarithm. And now we're going to go to step 2, which is rewrite this in exponential form. So we start at the base, which is 4, and we raise to the power, which is 1, and it's supposed to equal the result. So if I rewrite that, it looks like this. 4 to the 1, which is 4, is equal to 100 over x plus 1. Well, if I were to put 4 over 1 like this, now I have a proportion that I can just solve by doing the cross products. So if I do the cross products, I am multiplying 4 by x minus 1, which is 4x plus 4. I think I might have said x minus 1, but it was x plus 1, sorry. And then equals 1 times 100, which is 100. And all I have to do is solve that equation by subtracting 4. And that gives me 4x equals 96. And then I can just simply divide by 4. And that'll give me the value of x. So x is equal to 96 divided by 4, which I believe is 24. And now, you know, it's not a bad idea to check these. I mean, you can go ahead and substitute it back in, although they're not as easy to check as the exponential ones were to check, because especially if we're not in base 10. So, you know, might not be very easy to check. You just kind of have to play it by ear depending on the problem. If I substituted this back in, it would look like this. It would say the log base 4 of 100 minus the log base 4 of 24 plus 1, which is 25. And so it's not really readily available what 4 to what power is 100 or 4 to what power is 25. So checking this is probably not going to be something we're going to be able to do very easily. So just have to trust that what we did to solve worked. Or we would have to apply the quotient property here to rewrite this, which would be the log base 4 of 100 divided by 25, and it's supposed to equal 1, which if you raised 4 to the first power, it should equal 125ths, which is 4. So in some cases you can check it, it just takes a little bit of work. Okay, let's move on to example C. So example C wants me to solve log base 5 of x to the 4th equals 8. Well, right away I see where I could apply this power rule for logarithms, which says if I have an exponent on my log, I can bring it down in front and turn it into a coefficient. So it would look like this: 4 times the log base 5 of x equals 8. Well, the great thing about that being a coefficient now is I can just divide it right off both sides, and that just leaves me with the log base 5 of x equals 2. And now I go to exponential form. So when I go to exponential form, I start at the base, which is 5, raise it to the power, and that's supposed to equal x. Well, that means that 5 squared is what x must be, and that's 25. So x must be 25. All right, let's go ahead and turn the page. So example D is giving us an opportunity to use the product property for logarithms. So the product property is used when we have a sum of logs that have the same base. So that's the case here. And when you have two logs that are the same base that you're adding, you can rewrite it as a single logarithm of the product of the two results. So I could rewrite this as the log base 12 of x times x plus 1. Well, if I multiplied x times x plus 1, I'd actually get x squared plus x. And that's supposed to equal 1. Well, once I get this written as a single logarithm, which I've done, now I'm going to want to rewrite this in exponential form. So I start at the base, raise to the power, and it's supposed to equal the result. Well, 12 to the first is 12, and that's supposed to equal x squared plus x. Well, this is a quadratic equation, and we know to solve a quadratic equation, the goal is to put the equation in standard form with 0 on one side by itself. And so to do that, I'm just going to have to subtract 12 from both sides, and that leaves me with 0 is equal to x squared plus x minus 12. And this looks like this is one that can be factored. So I'm looking for factors of negative 12 that add to positive 1, because I've got a positive 1 right here for my b. So when I break this down, my two binomials are both going to start off with x, and I'm looking for factors of negative 12 that add to positive 1. And ones that come to mind are positive 4 and negative 3. So they multiply to negative 12, they add to positive 1. And my final step to solve is, then I look to see what would make each quantity equal to 0, and I know that negative 4 would make this 0, and positive 3 would make this 0. And so I've got my two solutions for x. X is equal to negative 4, and x is equal to positive 3. So what about example E? Now this time we have logs on both sides. So the temptation might be to try to get them on the same side together and combine them using one of our log properties. But the fact is, because I have a log on both sides and they're both the same base, so they're both base 10 because there's no base listed, then if they're supposed to be equivalent, what that tells me is that the results must be equal. So these two parts, x plus 9 and 2x minus 7, must be equal for these two log base 10s to be equal. So really all I have to do now is just solve this. It's just a real basic linear equation, and I'll get my answer. So I could subtract x from both sides, and that gives me 9 is equal to x minus 7, and then add 7 to both sides. And that tells me that x must be equal to 16. So I could go back and check that, because now this one is a base 10, so I'd be able to check that in my calculator. And I could plug 16 in there and there and check my work. Now, one thing you want to be a little bit cautious of when you're solving logarithmic equations, and I kind of thought twice about that when we were doing example D, because notice I got a negative answer in example D. I got -4. And if you think about if you have a positive base and you're raising it to a power, there's no way you could ever get a negative answer. But in the case of example D, -4 did actually work, because when you substituted it back in, you were actually squaring. See, like if you put it right back in here, you were squaring that -4, which made that a positive value. And then when you squared -4, you got 16, and you add a -4 to it, that gives you 12. And so it ends up working out. But just be cautious of that, and you want to make sure that you don't list a solution that actually doesn't check in the original. Now this final example, example 4, asks us to solve an exponential equation using a calculator. So we're going to leave this one to do together in class, and that way it's going to be easier to kind of show you how to use your calculator to do this if we're together. So we'll go ahead and end the lesson here, and we'll talk about solving with the calculator when I see you in class.